Is it running?
Yeah.
Yep. Go ahead.
So yeah, welcome all to this, I think, 17th in our series, Tunneling in QFT. Today we have Anna Kormu from the University of Helsinki, final year PhD student who has been working on simulations of bubble nucleation. Yeah, we don't yet have any more seminars lined up for July and August for the rest of summer. It might be that one pops up for July, it might not. But either way, we'll probably have a bit of a break in August and try to reboot again in September. But yeah, Anna, please take it away.
Okay, hello everyone, and this is Trouble in the Bubble, testing bubble nucleation calculations for strong phase transitions. And I'm really here to convince you why you should calculate your bubble nucleation rates non-perturbatively rather than using perturbation theory. This talk is intended more of a primer to the paper, so if you want all the nitty-gritty details, you can find the paper link right here on the first slide. So please go read that. But without further ado, let's get started. So I'm going to talk a bit about phase transitions, if I can. Hello? No? Aha, okay, there we go. So phase transitions are present in many places of our universe, such as the current unified theories, the electroweak, QCD, and so on. But I should maybe mention here that in the standard model of particle physics, the electroweak phase transition is a crossover rather than, for example, a first-order phase transition. But we also know that the standard model is incomplete, and in beyond the standard model physics, this first-order phase transition could very well be possible. And other things to look for from these phase transitions, beyond also the electroweak scale, are these topological defects, and then of course these bubbles from the electroweak phase transition. And here you can see a phase transition in the nature. This is rather just a Finland propaganda slide to convince you that it also, we also have shades of green and blue rather than just the tundra that people seem to think Finland has. But let's get started with the early universe phase transitions. So at about 100 GeV, we have the electroweak phase transition or the crossover in the standard model. And as a result of this phase transition, we have these bubbles nucleate and then start colliding with each other, creating a gravitational wave signal that could still be detectable even today. I'm going to briefly talk about different gravitational wave experiments that could reach the frequencies needed for these early universe phase transition, and also about the gravitational wave spectra and so on. So let's start with what are first order phase transitions. So here we have a field phi and the effective potential related to it. So the field phi goes through a phase transition. And when we are above the critical temperature and we start to cool down, so we have this primordial plasma soup that is very hot and dense, and we start to then drop down in temperature. And when we pass something called the critical temperature, when the phase transition happens, we develop two degenerate minima. And when we drop even below this critical temperature, we get this process called bubble nucleation, where we want to escape from the false vacuum state to the true vacuum state. And as this happens, we get these bubbles of the true vacuum that then expand and collide with each other. And as a result, we get gravitational waves, maybe. So I would also like to point out that I will be using the metastable state and false vacuum, and then the stable state and the true vacuum interchangeably throughout this talk. So if I refer to one or the other, just know that they are, in this context, the same thing. So one way of going through this potential barrier that the potential develops is to tunnel through it or thermally fluctuate above it to the true vacuum state. And as these bubbles then expand, that is what we want to study. How quickly does the nucleation process happen. And we are now going to talk briefly about gravitational waves as well. So gravitational waves are perturbations in the space-time geometry. So we have the regular metric plus some small perturbation, roughly speaking, and then the stochastic gravitational wave background is just a sum over the planar waves and the amplitudes and the polarizations, roughly speaking again. And this gravitational wave spectrum is usually modeled by broken power laws. And the main contributions that you would get from these early universe phase transitions, so these bubbles nucleating and colliding with each other in the early universe plasma, are the bubble wall collisions, sound waves in the surrounding plasma, and turbulence. And here you have a sort of a funny looking animation about a passing gravitational wave as it goes through in space, so you can see how it stretches and squeezes the space-time around it. I find this slightly disturbing, so I always have to, present it here. So what a first order phase transition might look like is pictured here. So here we have the sensitivity curves for LISA, and then also Desigo and Tianjin, and so on, which are these, well, Tianjin and LISA at least would be these space-based gravitational wave detectors. Then on the left, we have the pulsar timing arrays, and then to the right, we have LIGO, and so on. So the first order phase transition spectrum is expected to lie at the sensitivity range of LISA at the moment. But pulsar timing arrays are also an interesting experiment because they have actually detected these stochastic gravitational wave, or might have detected stochastic gravitational backgrounds, even if they are not from early universe phase transitions. So I am interested in looking at kind of these gravitational waves that would be from these bubbles. So again, looking at LISA, so the laser interferometer space antenna experiment, which is my favorite space triangle, which just orbits around the sun, trailing behind the Earth on a 20-degree angle. And here you can just see a quick animation of LISA going around the sun and the orbits that it draws when it rotates around. So this is something that could be interesting in the future to look at if LISA could actually see a signal from these first order phase transitions. So this is also partially the reason why we are looking into this. Then from pulsar timing arrays, like I already said, there's the hints of stochastic gravitational background from June 2023. And I always want to say a year ago, but it has definitely been more time than that. But this has been most likely from supermassive black holes, but they cannot rule out the new physics as of quite yet, at least. And pulsar timing arrays are just like the name suggests, the array of pulsars, and you can then time the electromagnetic beams as they arrive at the Earth. And here is the predicted curve that you would get from a stochastic gravitational wave background, and then the experiment data points on top of it, which quite nicely matches, I would say. But this is more to do with just as a general curiosity of why these stochastic gravitational wave backgrounds are interesting. So why is the bubble nucleation then important for these cosmological predictions of the stochastic gravitational wave background? So why on earth am I talking about this calculation and why you should do it as carefully as you can? So the basic gist of this is that you start with a particle physics model, and then you do dimensional reduction on this model. So you go from a 4-dimensional theory to a 3-dimensional effective reduced theory. I will talk a bit more about that just briefly to get you an idea what that is about. And after that, you should get these phase transition parameters from these bubble nucleation calculations, for example. So you have the transition temperature, the inverse duration of the transition, and the strength and the bubble wall speed. Then you plug those parameters into your real-time cosmological simulations to see how the bubbles grow and interact with the plasma and so on. And then you can model the cosmological gravitational wave background, this omega GV here. So all of these transition parameters depend on the bubble nucleation rate. And as you can see, for example, varying the beta, the inverse duration of the transition, brings the squishes down kind of the, what is that called? The signal. What is that in English? I'm completely blacking out.
Peak,
well, anyway,
spectrum?
Peak, thank you, spectrum, that's the word. So, and then for alpha, then that brings it up, and then temperature just kind of shifts it around a bit. So this is kind of the effect that the different phase transition parameters have on the shape of the gravitational wave spectrum, for example. And then the question is, how accurate are our cosmological predictions? Because here you can see, for example, that if you look at these gravitational wave spectra, you can see that there's quite a lot of uncertainty from this renormalization scale. So this reflects different choices for the renormalization scale. So there's a bit of uncertainty coming from the perturbative calculations due to this choice of renormalization. But the two loop is already much better here, as you can see. So the one loop really has the most uncertainty. And there's also these analog experiments going on, so you can test cosmology in a lab, which I think is quite neat. So you can test nucleation theory in the lab, because it's essentially the same in the lab and in cosmology. So there's the superfluid helium-3 experiments, there's this ferromagnetic superfluids, and also these proposals to test nucleation in other ultra-cold atomic gases. But I'm not an expert on this, so there's much more knowledgeable people in the audience, for example, at the moment. But I just think that this is an important aspect of these bubble nucleation calculations and how they are also of interest in the lab setting at the moment. So let's talk about these perturbative calculations a bit and move to the fate of the false vacuum. So at zero temperature, we have this relativistic field theory generalization by Callan and Coleman, and then the classical field theory with a complete one-loop calculation by Lange. So this finite temperature approach in quantum field theory is then introduced later by Affleck and Linde, and then there's these more recent studies of this are crucially showing that the nucleation rate factorizes by Olli and Jonas Hirvonen and Andreas Eksted. So you can write the nucleation rate as a product of this dynamical factor and this statistical factor. And the problem here is that in these perturbative calculations, that is not usually computed. So you have the dynamical plus the fluctuation determinant, and that is not usually computed in these perturbative calculations. And that introduces uncertainty, as we can see, for example, here. So perturbation theory depends on the details of the semiclassical approximation, and determining the prefactor to the dynamical parts is really, really difficult, even in perturbation theory. And so, like I already stated, this introduces then uncertainty and makes us maybe question how accurate are our cosmological predictions then actually. Luckily, you can also do this non-perturbatively. So you can do this real time, or as I like to call them, wait and see, because you quite literally simulate and wait and see until it has tunneled or not approaches that. And recently, there has also been works by Pervo and Battini et al. So those are quite interesting works, in my opinion. So I highly encourage you to look through them. But what I'm going to talk to you about today is this method that Kari Rummukainen and Guy Moore came up with in the early 2000s. So the rest of the talk will be heavily detailing how this bubble nucleation calculation actually goes on the lattice when you don't use these real-time evolution simulations. So basically, the point so far has been that these cosmological predictions have uncertainty in them, and it can depend on the renormalization scale, for example, as we can see here in the figure. And it would be important to narrow down how much uncertainty do these perturbative calculations actually introduce to our cosmological parameters, and if we could calibrate that error so we would know roughly the ballpark of the error that would be introduced. So key points, why you should care about what I'm about to say. So there's uncertainty in the perturbative estimates, and then the shape of the gravitational wave power spectrum. This also is important for baryogenesis, since bubble nucleation also plays a role in the baryogenesis process. Do not ask me more about that. I am not an expert on baryogenesis. Then there's also the analog experiments, and a lot of interesting progress has been made there. So let's talk about the real scalar theory. If you want to know more about the equilibrium physics, I encourage you highly to look through this paper. That's quite nice, all the details that you would need. So it's called the part 1 that Olli has been responsible for. And then we have this real scalar theory, and we are now looking at the bubble nucleation rate parts here in this second part of this series, so to speak. So we have this toy model that has all the key features of beyond the standard model theories. So it has a tree-level barrier, it's a strong phase transition, at least compared to the ones that have been studied before, that have been radiatively induced, like the cubic anisotropy model. That paper is from the early 2000s when people were looking at this for the first time. The perturbative expansion is also simpler, so we should understand the dynamics of this theory relatively well. So we start with this 4-dimensional theory. The Lagrangian is written down here, and then we have the interaction terms, so you can couple this to other theories, but we are just reading this as a toy model. Then you have the model parameters, and because you really do not want to simulate 4-dimensional fields on the lattice, you do something called dimensional reduction. So basically, at high temperatures, the system looks 3-dimensional. So you can actually go from a 4-dimensional theory to a 3-dimensional effective theory by integrating out the heavy modes, and then you match the correlation functions and build a 3-dimensional effective theory. And then you want to go from the 3-dimensional effective theory to your lattice discretized 3D theory, which looks like the following. So we have the sum over the sites and the lattice spacing A, the renormalization counter terms, and then the lattice formulation of the aforementioned parameters. And then you just throw this onto the lattice and let it run. Before I go through how exactly the calculation is built up on the lattice, I will also talk you through the generic idea behind this method that was developed in the early 2000s. So basically, the idea is that you have an order parameter, which doesn't need to be the true order parameter of the system. It just has to have something that has this two-peak behavior. So you can definitely kind of see this two-peak structure in your histograms, for example. But the most important thing is that it doesn't need to be the true order parameter. So one of the values does not have to be a 0, basically. So you start from the canonical ensemble, and you look at the free energy as a function of some order parameter. And as you see, this two-peak structure, you have the metastable phase and the stable phase and the mixed phase value between them. You don't have to pick whereabouts roughly your critical bubble will be. The simulation will do it for you. So as long as you have this two-peak structure, the order parameter dependence will even out later on in the calculation. So this is not an order parameter independent calculation. So what happens when you then go below the critical temperature is that the stable phase drops down, and we have again this rather familiar, at least to me, structure where you have to be able to go over this this peak here, basically. So what that means is that the configurations that exist at this peak value here determines the nucleation rate, or the upper limit of the nucleation rate. So what you have, you have the free energy barrier between the two phases. So due to the free energy cost of the interface separating the two phases. So this is in the canonical ensemble. And then you think about how many configurations do you actually have on your graph. So for example, if you have configurations that exist here, you're much more likely to tilt back to the metastable phase. Whereas if you are on the other side, you will just go back to the stable phase. But on the kind of a peak of the barrier, you have you're equally likely to go into either direction. And this is why the configurations that live on this peak of the barrier determine how much bubble nucleation you will see, or at least the upper limit of it, because this is just a statistical part of the bubble nucleation rate. And then you would need to add in the real-time evolution dynamics as well. So based on this, you can build up this Monte Carlo simulation where you simulate the probability distribution and of the order parameter. And it has this two-peak structure. So we are now just looking at, by the way, the probability. So this is then you just add a minus sign and you get the free energy essentially. So you would just tip it the other way around if you were looking at the free energy. But what you see here is that the metastable phase is quite unlikely compared to the stable phase. So, and in between we have this critical bubble value that is exponentially suppressed. So this is really, really difficult to simulate on the lattice if you use just traditional Monte Carlo. So what you would need to do in order to actually simulate these configurations that exist in this exponentially suppressed area, which then determine the statistical part of the nucleation rate, you have to use this multi-canonical Monte Carlo, where the idea is that you first do a Monte Carlo run just to generate the needed weight function to get the to sample the histogram if you don't unweight it as flat as you can, and then do a second run where you just sample the parameter space with the weight function on, so you can then have a flat, again, unweighted histogram, and then you can add in this weight information. And this is also how you can simulate this rather effectively. So you have this critical bubble area here, and that is, we draw these separatrix files or separatrix initial conditions from around this critical bubble area, because we want to use these critical bubbles as a initial condition for the real-time evolution. So what you need to do is calculate the probability of this critical bubble phase, and usually just normalize it to the probability of the metastable phase, and then you draw these separatrix configurations from a small area around the critical bubble peak. And after that, you have the statistical information needed, and you can move on to the real-time evolution part, where you can evolve a field configuration and see how the bubble evolves in time. So what you do is you have a field configuration as a starting point, and then you evolve it backwards and forwards in time and glue in the trajectories together. So here we have the small separatrix area that we draw the configurations from. So we have the order parameter and then the simulation time. The simulation time 0 just means that that is the starting point, and as we go backwards in time, we go to the negative direction. So we have reversed the momentum when we move backwards, so to speak. And you can then use these information to determine if your configuration has tunneled or not. So you have the metastable phase trajectory, for example, just starting from metastable and going back from metastable, but then we also have configurations that start from metastable and go to stable phase and vice versa. And from there, you can get this fraction of these trajectories that have tunneled and use that to calculate the tunneling fraction. So the tunneling fraction is just a delta function of the tunneled configurations divided by the time, how many times it actually fluctuates around that critical bubble area. And that is all you need for the tunneling fraction. Then the one more component that is needed in order to actually get this bubble nucleation rate correctly. So we have the statistical part that came from the Monte Carlo simulation of evaluating how probable these critical bubble configurations are, normalized to the metastable phase probability. Then we have these trajectories that determine how many of the configurations at the critical bubble configuration actually tunnel. And then we also need to know the flux, so the rate of the change of the order parameter. And this you can luckily also calculate analytically. This is also possible to do on the lattice, but you can also easily just calculate it analytically. So there's no need to do it on the lattice. So the flux is just the time, how quickly the order parameter, or how quickly it passes kind of through the critical bubble. And the result is that it's just a square root of some factors of pi and volume, and then this critical order parameter value. So the order parameter at critical bubble plus some constant a. I will tell a bit more about the constant a for you in a minute. So then you can compute the full rate, and you have this mystic 1.5 factor in front of it. So that is because you only want the configurations that actually start from the metastable phase and go to the stable phase, and not vice versa. So if you set up your simulation nicely, you should be about 50-50 in this which one started from the stable phase and which ended up in the metastable and vice versa. So you can just divide it away. So this is quite nice method of doing these calculations, but unfortunately it also has some, let's say, unfortunate lattice side effects, which is the order parameter you pick should be able to distinguish between the different phases. The problem is that the bulk fluctuations around the metastable phase grow with volume, and the critical bubble does not. So what can happen is that as you up your volume, which you would want to do in order to take the volume limit, for example, or just make sure that your configurations are actually bubbles or not some critical slabs or cylinders or potatoes, but it should actually look like a bubble as well. So what can happen is that the symmetric phase bulk fluctuations, as they grow with volume, they start to bury under the critical bubble branch. And what happens is that then when you look at your histograms, for example, and try to calculate your bubble nucleation rate, you can see that these bulk fluctuations cut off the critical bubble branch. And that's rather unfortunate. And we first started doing these simulations with using this linear order parameter, which is just a volume average of phi. And as it turns out, if you pick that, it's quite prominent, this behavior where the critical bubble branch just gets kind of squished under the bulk fluctuations. So we moved to this kind of improved order parameter that is just then the volume averaged phi squared minus this 2a and then the volume averaged phi again. So this a is just some constant that you pick. We picked it to be the symmetric or metastable peak maximum. That seems to fix it quite nicely. At least you can go to higher volumes. So in order to actually do these simulations, you have to be kind of careful with the, let's say, numerically sensitive choices that you have to make. And this is something that can then, of course, delay your work quite unfortunately, because it's a lot of simulations to run. So let's move into results. And I have been super quick today, I see from the time. I usually probably talk a bit more about the introduction bit, but apparently it's too close to midsummer here in Finland, so apologies for that. So here we have the continuum and volume limits. And if you look at this, so we have the lattice spacing, and then on the y-axis we have the logarithm of the nucleation rate. So we use something called order A squared, improved lattice discretization. So the leading dependence on the lattice spacing should arise at A to the third. So we fix the volume and then we vary the lattice spacing. So as you can see, we have fitted this cubic fit here. It's a least squares fit. And as we can see, this if you would fit all the points, the error is quite dominated by this A is 3.5, and that is because it goes well beyond it's approximately the inverse screening mass of the system. So we expect the cubic form to break down there. So therefore, when we fit into just these points that are well below the screening mass, we see that we get quite nice behavior already at A is 1.5. So we take the continuum limit that we are close enough to the continuum limit already at 1.5. You might be wondering, what is this point here? Well, that is all the parameters suffering from bulk fluctuations. So you can still do the calculation, but it just if it's not buried under the bulk fluctuations too much, you can still do the calculation, but you will get higher error bars. So in order to reduce the error, we moved into these improved order parameter to the improved order parameter. So from there, we then go to the infinite volume limit, where A is 1.5, and we vary the volume. So the Euclidean model has no massless mode, so the long-range correlations die off exponentially with distance. So you can actually then fit something exponential based on that. And we can see that this matches quite nicely. You can also do a polynomial fit, but if you look at then the chi-squared test, for example, it yields much worse results. So the exponential form really seems to be the correct one here. Also, as it is kind of more physically relevant for this plot. So from there, we can then get to our final result, which is this minus 7409 in logarithmic space. And that is the answer, or the main key result of our paper. Now, you might be wondering, how does this then compare to the perturbation theory estimates? And the answer is here. So we have the inoculation rate, or the logarithm of it, as a function of temperature. And here we have the lattice simulation point that we actually have here on the little orange triangle. And then we have these other lattice points re-weighted from the histograms to also other temperatures. And here we see that the tree level is quite far away from our result. So the tree level means that it's the functional determinant and the dynamic prefactor are approximated as t to the fourth. Then in the LPA, so this second line from the top here, this is the local potential approximation. And here you can do different things to these imaginary parts that turn up in your calculations. So there's different ways of dealing with these imaginary terms that turn up. So this just sort of reflects the choices that you can make to get rid of them. So those are the error bands here. Then you have the one loop estimate. So this is a full one loop calculation that you can get, for example, from bubble det, where also the dynamical information is there. And here you can see that the lattice and one loop results agree with each other quite nicely qualitatively. So the shape of the curves is quite nicely the same. Unfortunately, for lattice, for one loop at least, they are quite far off from each other. So there is a 20% difference in logarithmic gamma, which means it's 10 to the several in gamma. And there are a couple of reasons why that might be the case. So there's the question of, do we fully understand bubble nucleations, first of all? So the tree level is 100% away. One loop is 20% away in logarithmic gamma. So it's quite a lot of discrepancy between the two, but the shape is the same. So at least qualitatively, they do agree. So the system should be well described by one loop, because if you look at this latent heat, for example, so we have something that is proportional to latent heat here, and then you have the loop expansion parameter, and this is our simulation point. So this is from the previous paper by Olli. And we chose this simulation point because we knew that there's also already really good agreement in latent heat on the lattice versus one loop, and they agree within 1% in linear space. And then when you put the same parameter point to the lattice, you are suddenly 20% away in logarithmic space, which is quite far away. So there are a couple of things that could be going on. So maybe the semiclassical approximation just breaks down. Maybe there's other relevant saddle points that you should consider in the calculation. Or maybe you just have to just go to the next loop order because this non-equilibrium physics is a lot harder to capture. So maybe that is the most likely explanation here. And with that, I would like to move into the conclusions and just state that these results allow us to calibrate the uncertainty in these phase transition parameters when obtained from perturbative results. And these accurate calculations of the nucleation rate are crucial for calculating the gradation wave power spectrum, and we show a suppressant of by a factor of 20 compared to the one loop estimates. And if you remember only one thing from this talk and nothing else, this is what I would like you to remember. So nucleation rate calculations are inaccurate in perturbation theory, and lattice is significantly better. Thank you.
Thank you very much, Anna. Thanks a lot for that very nice talk. Yeah, I'm going to open the floor up now to questions. So yeah, please raise your hand or unmute yourself if you have any questions for Anna. Ian.
Well, thank you. That was really clear and very lovely. I'm not sure this question makes sense, but are these differences in the nucleation rate, are they entirely due to the prefactor? Or does that question not make sense in the sense that it's not clear what is in the exponent and what is in the prefactor?
Well, if you think about that, so you can factorize the bubble nucleation rate quite nicely, right? But there's some tiny details that go into the factorization, so it's not exactly one-to-one when you compare, for example, from the lattice to the perturbation theory. So I am not actually entirely sure how much of the sort of how much the dynamical information sort of from the perturbation theory matches the dynamical information of the lattice calculations. Now, Olli, do you remember? Because I do not.
No, not quite. So
Yeah.
yeah. So there's basically a different split between prefactor and exponent on the lattice side and on the perturbative side.
And how does it go? It's
But it's a fair question. What is prefactor? Maybe there's a better place to expand around than the exponent, something like that.
And you can compare the, if you just look at the flux, for example, so the flux times the statistical information, you can sort of get a rough estimate from there. So even if you would kind of completely disregard the dynamical real-time simulation part of this lattice part, you can still just kind of get a upper limit for the rate from the flux times the statistical part. But the problem then is that it's slightly dependent on, for example, the sampling rate, like the dt that turns up in the flux. So
there's one thing to look at in the experiments, but is parameter dependence. Now you've shown dependence on temperature, and are all the other parameters scaled out so that all you have left is the lambda 3? Is that the point?
yes. So basically, all the parameters are tied to the temperature, right? So we are just showing how it changes as a function of the temperature.
I'm just thinking, what were the best thing to tell the experimentalist to measure to try and see if there's any agreement with the results?
I must admit that I don't think I am that well aware of all the details in the experimental side of things. I cannot comment on that from the top of my head, unfortunately. I would need to reread some of the papers to better remember what was the suggestion to go
It's
with.
still an unfair question.
Yeah.
What I find with experimentalists, it's very difficult for them to measure the precise values of parameters. What they can usually do is look at the relative values of parameters. So they can say, if I double the temperature, then the nucleation rate, increases by a certain factor.
Yeah, sorry, what was your question again?
I'm just wondering
Yeah.
what we should ask experimentalists to do. And it's a bit unfair because you're not an experimentalist, but what would it be useful for them to measure if you wanted to test the theory?
So I'm not sure, how do you do the you do simulations, right, on the experimental side as well? And is there a discrepancy between the simulations and the, I guess, has the lab set up, how far is that from the realization, I suppose? And is there a way of maybe comparing those, like a simulation somehow to what we are doing now? That would, I guess, be my first question.
Yeah, well, we do real-time simulations, of course. Yeah, that's right. But the same thing goes there. For example, we give up on the prefactor, the hard bit that you're trying to do, and we look at how the rates depend on various parameters, assuming that the prefactor is not changing very much. And then you can sort of, for example, verify that the log of the nucleation rate goes like, goes like one on the temperature, things like that. Which of course are violated when you put in the proper dependence of the prefactor, or when you do the calculation properly, you're going beyond those very crude approximations.
From the top of my head, I don't think I can comment on that, unfortunately.
Yeah, it's
It's
rather,
a very,
rather
very
unfair,
difficult question to ask.
yeah,
It's a good question, though. I would like to know myself. So,
Can I ask one question about this slide? So I'm not sure if I'm understanding correctly, but according to this slide, it seems that lattice fully agrees with the one loop calculation. Like the black points are within the...
yeah, so this is an equilibrium. So when you have the peaks are the equal height. So this is, not below the critical temperature. So this is the latent heat then. So I would expect that perturbation theory would function a bit better when you have equilibrium physics going on. So that's the kind of reason here. To be fair, I think we expected to find better agreement when we set up doing this, and it's one of the reasons why this simulation point is picked, because it agrees so well in equilibrium. So it would have been nice if it had also agreed at the bubble nucleation rate.
So, in other words, this is just checking the metastable state, like a thermal state of in the metastable regime.
Yes, I believe so.
Yeah, okay, got it, thanks.
Precisely this delta phi is the different distance between the metastable and the stable phases. Any final questions? If not, then let's thank Anna again, and
Thank you.
thank you very much, everyone. Thanks a lot, Anna.